I can get going. Is the recording set up? Okay, thanks. Okay, welcome all to this talk, non-math introduction to zero knowledge proofs. This is a slight lie. We do get into some of the maths, but I'm just kind of trying to reset the focus and things we're highlighting, and try and give you intuition for how you can actually apply this technology. I do some zero knowledge stuff at the Ethereum Foundation. I made some circuits there, and I was also involved at the privacy focused layer 1 called Alio. So I'm going to dig in. We're just outlining what we're going to be doing here. I think it's around 45 minutes speaking, and then there'll be time for questions at the end. And like I said, I want to focus on what we can do with the technology. I want to try and give people the understanding and intuition for like how you can apply this technology to solving business problems. So not just for mathematicians. So also this talk is also for people who are experts and are just looking for educational analogies and ways to present this topic to people. So I've got some of the quotes here, and like, you can prove anything with ZKP. It's some of the messaging I've seen which it's not really very accurate. And I also have a video on YouTube with this like basically title, so I'm kind of hypocritical here. It's kind of fair enough to have a clickbaity title as long as you try and right the wrongs of how you find how the technology works. But then this second statement is like something that I find so ridiculous. You can prove that you know something without revealing that you know, without revealing the thing that you know. So this is the statement a lot of us make, and this statement is like completely confirmatory rather than explanatory. If you tell this statement to somebody who doesn't know about technology, I don't think anybody's ever been like, oh yeah, great, that makes so much sense. Like, it doesn't really click for anybody. All this statement really does is tell other people who know about this technology that you also know this technology. So it has like value as showing you're part of the in-group, but it doesn't actually help explain the technology to people. And I want to try and give more explanatory context. Yeah. Starting place is just like, why do people actually care and about this technology? The first main one, of course, is scalability, where transactions per second, gas cost, and just doing more stuff on chain, opening up applications. And this is also one of the places where we have kind of bad naming of the technology. So there's the ZK-EVM, there's ZK-Sync, and a bunch of others where the only property they're using in this technology is the scalability property and not the zero knowledge property. So like kind of badly named, which is the same thing as that statement I gave before. You can prove that you know something without revealing the thing that you know. Like, this isn't the case. This is like you're giving one property of a zero knowledge proof. And in a lot of the big use cases, this isn't even the property that we're using in technology. So it's kind of like really bad messaging. The second one, obviously, zero knowledge privacy aspect, where you can hide more information than we did before. And this is important for like personal safety and national security and freedom. I'm quite interested in politics, so these are the kind of things I find very interesting. I will also give you an additional story of how bad things can be when you are lacking privacy. Now, this isn't a digital privacy topic, but it's kind of a very interesting story related to privacy to try and maybe seed your knowledge of some of the debate there. So, okay, in the Netherlands in the 1940s, the guy in charge of statistics there, the guy likes statistics, he likes data, he wants things to be organized and efficient. So he had this plan, and he wanted to give every Dutch citizen an ID card, and then he proposed it to the government, and the government said, like, that goes against our democratic foundation, so we're not going to do that. A few years later, the Nazis invade, and then same guy proposed the idea to the Nazis, and the Nazis were like, oh yeah, great idea, give everybody an ID card. And then, of course, on these ID cards, every Jewish person has a J on their card. Now, I can't think of an easier way for a roaming, Nazi soldier to identify somebody as Jewish. Just ask for their card. There's no questions or anything. Then in France, when the Nazis invaded France, then they asked the French, and they said, like, how many Jewish people live here and where do they live? And the French were like, we have no idea how many live here, and we definitely don't know where they live, because they didn't collect this information. Okay, someone's asking about the max number of participants. By the way, I am the chat open, so if there are questions along the way, I can pause and answer them. I'm wondering whether I should pause now if there's like a problem of other people joining the room. Okay, sure.
Are we at the max capacity for the room though?
Yeah, I don't know.
Okay. So
okay, I guess somebody can give confirmation if other people are actually struggling to get in. Okay, somebody can't get in.
Someone who can't get in.
Okay, then I can pause here to try and solve this. Should I pause or should I just kind of continue because I don't know who's solving it and Sure. Okay, so and then in France, the Nazis asked them about this data. They didn't have it. And they forced the French to do a census in 1941, and this is where they go around and collect data from the entire population to work out demographics. We need this to know how many MPs to dedicate to different areas and stuff like that. But they try to sneak in a question to figure out who is Jewish, and they ask like, who are your grandparents? And the Nazis obviously didn't know this, but the French guy in charge of the census was a member of the French resistance. They used this census to make 20,000 fake identities for people, identify people who might have been willing to join the French resistance, and then all this data on who was Jewish and where they were was never even tabulated. They didn't even collate it and collect the data. Unfortunately, this guy was eventually found out in 1944, sent to Dachau, and he died shortly before the end of the war. But the takeaway here is the Netherlands had the highest death rate of Jews in Europe. They had 73% of their Jewish population were murdered, and then in France, 25% of their Jewish population were murdered. Now, the Netherlands is a smaller country, so the statistics can be skewed, and there's of course other factors at play here. But I can't imagine that this one thing where Dutch citizens have to carry around an ID card that has a J on it didn't contribute massively to this massive disparity. So there's not really a digital world, real current world example of the importance of privacy, but it just shows how bad things can get. And I think it's important to like recognize some of the things to keep privacy. So I wrote some blog posts about this as well, but that's just one thing to go. And then we're going to go into the zero knowledge aspects now. In terms of educational content for zero knowledge, mostly it is these really basic examples, which are super great to get started with, and then like jumps all the way to finite field elements and polynomials and all this kind of hardcore stuff. And there's not really anything in the middle, and this is the gap I'm trying to bridge. So the starting analogies, we have ID at a bar. This is where you go to a bar, you want to have a drink, and in order to, you have to show your ID card. But it gives away not just that you're old enough to drink, but your specific date of birth and your age. It gives away your entire name. It may give away your address. And the point of this analogy is it just kind of sets the scene for privacy and showing that you don't have to provide all this data. The only data that's needed was that you're old enough to drink. But it doesn't really tell you anything about technology. So that's one of the starting examples. Then there's Alibaba's cave. I'm sure many of you know about most of these. So in this one, we have there's Victor and Peggy. Peggy's the prover. We have this cave that's kind of circular. And at the end, there's this door. There's this door here. And it's a magical door, and it has a secret phrase to go through. And Peggy wants to prove that she knows the secret phrase. So what happens is Victor looks away, and Peggy goes into whichever corridor of the cave that she wants. Then when she's in there, Victor goes and shouts at random A or B. Now if he shouts A, Peggy has to come back down path A. If he shouts B, Peggy has to come back down path B. Now if Victor shouts A and Peggy comes back from path A, then maybe she knew the secret passphrase because she was on side B and went through the door, or maybe she just got lucky. Victor wouldn't be very convinced. But if you repeat this 10 or 15 or 20 times, then you get like to a scenario where it's basically realistically impossible that we got lucky that many times. And this is how some old zero-knowledge proof systems worked. It's obviously like less efficient. You've got to repeat the process. These things were much slower. We have better systems now, but this is a decent analogy to show the idea, which is that they prove something without similar with where's Wally. In this one, I can prove to you that I know where Wally is age without actually pointing to him. So if we're in a room together, I will I'll take a phone from one of you at random. I'll ask you all to turn around and look the other way, and then I'll take a close-up photo of Wally, but with like no surrounding information, and then you so that you can work out where the image, where page they are, and then I get you to turn back around and I show you the image. And you can look at the metadata and other stuff as well if you want. And you'll basically be convinced that the only way I would take a photo is if I actually knew where Wally was on the page. So these are like really nice to get like some of the core ideas of the technology, the zero knowledge side of things. And they're quite memorable because they're just nice stories. But there's nothing there in terms of like, how does the technology actually work? And if we have this problem, business problem that you want to solve, and you're thinking about using zero knowledge technology, how do you like generalize the knowledge from this analogy to solve that problem? It doesn't really work, and you have to get some more data. So, what do zero knowledge circuits actually do? And this is what the focus should be: is something called circuit satisfiability. So a zero knowledge proof is some piece of data that proves that some computational circuit was filled out correctly. So here's the statement. We're now going to go through these definitions and understand those in a bit more detail, and then we're going to go back to statement and have another look at it and see what that it makes sense. Because right now these are probably like new terms and like less well defined, and then we're going to go into some example cases to see how it's applied. Okay, so for circuits, we're going to start with like normal computers. You probably have a rough understanding or idea of what a circuit might be, and we're going to start with the gates in the circuit. So you may or may not know this, but in normal computers, a gate is a NAND gate. I think this is true. I mean, it was true. If I'm wrong, maybe somebody can correct me. But you'll have just NAND gates. Before we do a NAND gate, we'll do an AND gate. So this is an AND gate, 2 in, 1 out, X and Y go in, Z comes out. Errors are ones or true and false. And an AND gate just says if both the inputs are true, then the output is 0. And that's what we have in this table here. Okay, these are the only kind of legal combinations of values for this gate. Then for a NAND gate, it's the same thing, but you just take the AND thing and then you negate it. So an AND gate, if it takes in 2 trues, it outputs true and is otherwise false. So then for a NAND gate, you're going to take in 2 trues will give out false, and if not, it'll give out trues. Okay, so this is a gate in like a normal computer, a NAND gate. And then we want to put these together into a circuit. So you just lay out some of these gates, and you're going to connect up the wires. And a circuit is just a collection of gates with the wires connected in whatever fashion makes sense. You probably had a rough idea of circuits, but I just want to like touch base and like so we're all on the same page. If you want to learn a little bit more about this, before that. Think about what you can do with these computational circuits. So obviously you're using a computer right now and it's doing all this crazy stuff. So clearly you can make these circuits do loads of things. But we're going to want to think about more specific examples related to the real world. Like maybe it's withdrawing money from an account, could be analyzing some data, and then maybe you can find some other examples too. So I have a mathematics background. I didn't do computer science, but I read this book and it's really, really good. It's for people who don't know computer architecture. And the guy, really good, well-written, popular book, he just talks you through like how to actually physically build a computer from scratch. So it's a really shitty computer, but it shows you the core things, and a CPU and then a RAM and everything else is a peripheral. So reading this book was really, really helpful to see my understanding of like how a computer works. I'm not a computer science student, and maybe some of you are similar. Then in the zero knowledge case, we're going to take the idea of gates and circuits, modify them for how they work in our scenario. So instead of NAND gates, addition gates. We're all going to be 2 in, 2 wide, 1 wire out. So addition takes in A and B, output C. Multiplication takes in A and B, output C. What are the wire values? So previously we had binary. It was the true and false or zeros and ones. Now we're going to be using numbers. Now, if you really, really hate numbers and maths, you can just imagine these as all whole numbers. So 0, 5, 10, -5, up to, infinity, a million, minus million. And that, you don't need this stuff to apply the technology as a business person. But it is helpful to understand this aspect of things. So we're going to briefly touch on finite fields. And I'm sure most of you probably know this anyway, so we won't spend too long. But the starting place, the idea is it's like numbers in a clock. So if it's 10 a.m. and 4 hours pass, then we'd say 1400 in Europe, some of us, but it's also 2 p.m. And how do you know it's 2 p.m.? Well, because you know that if it's 14, but you just take away 12, so you end up at 2. Okay, so this circular wrapping around the numbers is exactly how finite fields work. The only important difference is that the total number of numbers in a clock is 12. In a finite field, it always has to be a prime number. So, we can't have 12, but we can have 13. Okay, now fields are, there's loads of complexity and loads of theories and lemmas and all this kind of mathematical stuff. But you don't need any of that really to make zero-knowledge circuits. You just need the idea, the definition of them. Just a few examples, just so people have seen some, in case they haven't before. Let's take our prime P to be 13, and then I'll just walk through these with you. If we have 5 plus 15, well, 20, but 20 is not between 0 and 12, so 20 minus 13, we get out 7, so the answer is 7. 5 times by 9 is 45, but we need it to be between 0 and 12, so 45 take away 13 is 32. 32 take away 13 is 19, I think. Brain doesn't work very well right now. And 19 take away 13 is 6. So you kind of, bring it back between 0 and 12. The same as 13, we won't have 13 because the size of the set is 13. But we don't go from 0 to 13, we go from 0 to 12. Instead of 13, we have 0. Because you can have 13 minus 13, you get 0. And minus 1, we're going to add instead of take away. So minus 1 plus 13 is 12. Okay, just very briefly, I'm sure most of you know this already. There's some other ones on there for people to look at later. And then this slide just has the answers for people looking at this in the future. There's also the notation we use in this image. We have A, B, and C, and then this kind of E thing is an element of F, and this is mathematical shorthand for a field. This F with a double line just means field. And then again, the field equals the number, the set from 0. I know this is an O, but it's supposed to be a 0, up until P, whatever our prime P is. In our last example, it was 13. Now the square bracket here on the left, this means include the number, so it includes the number 0. But the parentheses on the right, this means don't include that number. So it doesn't go up to P, it goes up to P minus 1. And that's all you need to know about finite fields, really. It is also a good time to point out one detail that about how things work in zero knowledge. There's zero knowledge specific hash functions. So Poseidon is I think the most popular one. And why not just use a normal hash function like SHA? The reason is SHA was designed for the native numbers to be binary, to be zeros and ones or true and false. So you can do that in a zero knowledge circuit, but the numbers aren't natively binary. They're natively field elements between 0 and whatever your prime P is. So then you would have to constrain all these field elements to be binary, to be 0, 1. And this takes some constraints. You're putting in some gates already, so you're already growing the circuit. And then to do the binary operations, the NAND gate or whatever it should be, this is going to take even more gates because it's not like a natural gate per se. It's not an additional multiplication gate. So you can emulate normal hash function in a zero circuit, but you have to emulate it and the cost blows up. So we ideally want them to be faster, so we have zero-knowledge specific functions, and these are designed with field elements and with these additional multiplication gates. Zero-knowledge technology has existed for like 30 years or so, but it's only just now becoming computationally feasible to make use of it in the past few years, and making circuits faster is still a big challenge. So this is like an important aspect to keep in mind. Okay, then previously with NAND gates, remember we were connecting up the wires, but NAND gates are like physical. In your computer you have actual gates there with actual wires connecting them. These gates in zero knowledge, they're ephemeral. They don't really exist. They exist in our minds by the way we deal with the numbers going on in the computer. So if we want to connect, then anything to connect. So what we do instead is that you see in this example here, we've got two gates, addition multiplication. In addition, we have A and B go in, left wire, right wire, and the output. And now the multiplication gate, the input is left wire C and right wire D, and the output is E. Obviously, I mean these two C's to be the same. The way we make them the same in zero knowledge is what we'll do is we'll take the circuit and the wire values, and we'll make a copy of it. And in the copy, we will swap the values that we claim are the same, that are the wires that are connected. Okay, and then within the proof system, you kind of like juggle these around, and if they're not actually the same, if the wires aren't actually connected, the proof will fail. But the idea is the same. You're just connecting up wires, but instead of connecting with a wire, you just you just swap the numbers around that you claim to be the same. And then I've got this dashed line here, so you can connect as many wires together as possible. Maybe this output addition gate goes into 100 other gates. It can be arbitrary number. One caveat for the explaining that I'm going through here: zero-knowledge proof systems are quite complex and complicated, and if we try to just explain everything generic in the beginning, it just like we wouldn't go very far with people. Everybody would be so confused from the beginning. It makes a lot more sense to just take one proof system and understand it in vertical in full. And I'm doing this with PLONK, because once you understand one system in much more detail, then proof systems are quite modular. So you can just start learning a new piece and swapping it out and putting it in. So it's better just to learn one proof system properly and then kind of branch out from there. Horizontally. And I think PLONK is like very pedagogically good, easy to start with. It's also used a lot. It's the PLONK stuff is used in Halo 2 a bunch, which is used by the Ethereum Foundation and Zcash and some other places. This is a good one to start with. Recap: a zero-knowledge circuit is just these gates, additional multiplication gates placed around and connected up with these permutations. I want to emphasize as well that if you have the same gates, but they're connected, even if one wire value is connected differently, then these are like different circuits. Okay? So a circuit is very specific. It's exactly all the types of gates and exactly how they're connected. Going back to our original statement, like what actually is a zero-knowledge proof? Well, this proof, little pi here, we usually use pi to denote it, is some bit of data, and you check it if it's valid or not. And if the proof is valid, then what it says is that you filled in some circuit in a valid way. This means that there was already a circuit that existed. There were already gates and wires connected however way, but all the wire values are what you put in place. And if you do this in a valid way, it means that if you have an addition gate and you have A and B go in, the only possible thing that C can be is the addition of A and B. And in the multiplication gate, the only possible thing that E can be is the multiplication of C and D. So this is what the proof says. You fill this circuit in a valid way. Okay? And the value of this is going to be like what the circuit says about the outside world. One other thing is that the prover can reveal whichever wire values they want. Maybe you just tell me the wire value E, so then I check your proof and I say this is valid, and you get out E. And this way I know that you know three numbers such that if you add two of them and multiply it by the next one, you get out E, and let's say it's 17. I don't really care about that computation right now, but it's a dummy computation. We're going to go into some more useful examples soon. Last 2 points before we go to the examples. How do you make a proof? What information do you need? Well, you need the circuit, so you need to know how many gates and what types are they, and then how are their wires connected. And then you also need to know all the wire values. I mean, remember, the proof is a statement that you know all the wire values, and it's a valid combination of wire values. This is sometimes referred to as the proving key. So you'll need all this data to make the proof. So it's the proving key. It's the thing that helps you unlock it or something. Then that's for proving, and then for verifying. What do you need to know about verifying? You need to know the circuit, right? Because remember, the proof is a statement that you filled in the wire values correctly for some circuit. So we have to know what circuit that is. So how many additional multiplication gates and how are they connected? And then you need to know the public wire values. Okay, what wire values is the prover revealing to you? And then what value of design proofs? Like I said, it's about what does it tell us about the outside world, the real world. For example, if you don't reveal any wire values, there aren't any public wire values, and you give me a proof, and when I verify your proof, all it tells me is that you filled in some computation. I know what the computation is. Maybe it was a hash function. If you filled in a hash function in a valid way, I don't care. You haven't told me anything of value. You can put in any number and get out any other number. There's no value there because you haven't shared with me something more specific about the real world. You've just solved put in some input for that function. But if you make a zero-knowledge proof of this hash function and you tell me what the output is, then I have a proof that says you know the secret key to this public key, i.e. you're the owner of this account. Now that has some value, possibly, depending on the public key. Maybe it's one with loads of money or something like that. So what does the circuit tell us about the world? This is where the value comes from. And going the other way, how do you use zero-knowledge proofs to solve a business problem? Well, you've got to figure out what does the circuit have to say about the real world in order for this problem to be solved. So I think we can dig into the examples now. This explanation is kind of different to a lot of the other zero-knowledge proof explainers I've seen out there that dive into maths and polynomials and how zero-knowledge proofs work. I don't think that matters for the vast majority of people. I think to spread technology more widely, we need business people and developers who just understand the interface and not what's happening under the hood. The same as the internet. I don't know what the internet's doing, or Wi-Fi. I'm sure most people don't, but I know how to use it. I know what I can do with it, and that's the kind of interface focus that I think most people should try and take. So for our first example, there's the RSA factoring challenge. I'm sure many of you have heard of RSA before. It's an encryption communication protocol they've been using for decades online so that me or you can speak with somebody else online. Maybe you want to speak with your bank online, and it helps make a secure line between you. The way it works is that you will come up with a massive random prime called P, and your bank will come up with another massive prime called Q, and then you'll do some exchange mechanism, and you'll end up with PQ. Now, any eavesdropper who's trying to listen in, they won't find out P or Q, but PQ will be publicly known. Again, I'm sure most of you know this, but I'm just clarifying. If you know PQ, you can't find the factors P and Q. You can't find factors P and Q that made PQ. Now, there's no mechanical proof of this, but people have been trying for thousands of years, and they're pretty sure that the only way to factor numbers is brute force. But brute force is kind of computationally bounded based on what's realistic. So if you make P and Q big enough, then it's going to be literally impossible for anybody to factor those numbers. As computers get better over time and some of our algorithms get better over time, the size of PQ might have to grow. And just to get some rough idea of how good we are, there's the RSA factor challenge. And what they do is, I can't remember who runs it, but they just put out a bunch of numbers, PQ values, and you have to just try and figure out what P is or what Q is. Okay, and for some of them you have a cash prize. So this is just a screenshot from Wikipedia. There's all these numbers. Many of them solved. Last one 2020. That last one 2020 was RSA 250, and 250 decimal digits. That's like loads. But the one we want to focus on for this example is RSA 896 at the bottom here. Cash prize $75,000. Really nice. 270 decimal digits, so like base 10 and not base 2, and that's like such a big number. So the universe has like 10 to the 80 atoms in it. 270 digits, decimal digits. It's like having our universe, every atom in our universe, but every atom in our universe is also a universe, and every atom in those universes is also a universe. So it's like our universe cubed, which I can't even begin to fathom how large that is. It's just like so ridiculous. So computationally, like very, very extremely hard to solve this kind of stuff. So let's say that you solve this and there's a cash prize, $75,000, but you're really skeptical and you're worried that if you tell people, they might steal your results and they'll take your money from you. So what can you do? You can make a zero knowledge proof. Okay. So what do you want the zero knowledge proof to tell you? And we're trying to think about how to use this to solve problems. So if we want to use a zero knowledge proof, then we kind of want some circuit that proves that we multiply two numbers and get out RSA 896. Okay. So it's fairly straightforward circuit, right? We're just going to have a multiplication gate. We're going to left input y p, right input y q, could be the other way around, doesn't matter. Output R896. Now, if you do this, and then you make a proof, and then I can verify the proof, and everybody else can verify the proof, because what should be the public y values, the y values that you share. Obviously, you don't want to reveal P and Q. Those are exactly the things you're trying to hide. But you want to share RSA 896. We want to know that the number that you multiplied to get is this public number that people are asking factors of. And then we can all verify it. Hey, congratulations, you solved this problem. You get $75,000. But not quite. Okay, so there's going to be different kind of bugs that you might have in making zero knowledge circuits compared to programming in other areas. This isn't actually quite true because there's another value combination to this gate or this circuit where you don't need to know P and Q. And many of you probably realize you could, instead of having P and Q, you could just have 1 and RSA 896. Because 1 times by RSA 896 is still RSA 896. So this circuit has to be more than one gate. There's a few ways you can do this. You can check that both numbers aren't 1. You can check that both numbers aren't RSA 896. Or you could check that P is neither 1 or RSA 896. Okay, so here we want to, what we want to do is, on the left here, I've got this P, and it goes into this square gate that says I know, and the output is 1. I made a square, not a circle, because it's not actually a gate, it's a collection of gates. It's a sub-circuit. The I know means is not 1. So what this part is doing is it's checking that P is not 1. And these sub-circuits, we usually refer to them as gadgets. These are things that these are like common structures that you're going to want to use in lots of different circuits. So checking a number is not 1, probably you'll have to use it occasionally in other circuits as well. So rather than always re-implementing it yourself, you're just going to use a gadget that some other really smart person made and it was secure. And then the output is going to be 1, and this should also be a public wire value because is not 1 just says true or false based on whether it's 1 or not, and you want to check that it is true that it's not 1, so it should output 1. And then we have this dash line. Remember again that this is the connecting up the wires. So these two P values should be the same. Repeat the same thing on the other side. Q, and then here's one, and now it's found the public values of these outputted ones and the RSA896. Now we have a proof that says you know two numbers that when you multiply them together, you get RSA896, and neither of these numbers is 1. So now the only reasonable conclusion from this is that you solved the RSA factoring challenge. Okay? So this is like a kind of starting simpler example where there's not too much going on in the circuit. Second example, let's say that you're Satoshi and you want to prove it. There's loads of ways to prove it, but we can use zero-knowledge proofs because it's an example. More specifically, you want to prove that you're the owner of the public key, because then maybe you're Satoshi. So I'm sure you'll know you derive the public key by hashing the secret key. So if we want to make a proof that shows that we're Satoshi, then we want a circuit that shows that you know the secret key and that the output is the public key. So I'm sure many of you can work out that the circuit should be, again, remember, it's a square, it's a gadget, H for hash, and you're going to take in the secret key and you're going to output Satoshi's public key. And the things that should be public values here, which should only be Satoshi's public key, right? You don't want to share anything else. So then if you see this proof and it's valid and the output public key is Satoshi's public key, then like what the circuit says, what the proof says, the value in the real world, it says that you know the secret key. It doesn't say that you are Satoshi. You know, you could be Satoshi, but it just tells people that maybe you actually are him. Maybe you got lucky finding it on the dark web or something. Maybe you figured it out, but that should be computationally impossible. Otherwise, the hash function would be broken. Okay, but so again, the one thing I want you to think about is like, what does the circuit and the proof tell us about the real world, and why is that valuable? Okay, just going to check. Okay, I think we've been going for about 35 minutes. Maybe 10, 15 minutes left. Third example, ZK-EVM. This is one of the things I mentioned before. They're trying to, turn Ethereum, and instead of make all the blocks, instead of if you want to be a full node and you want to join the entire chain is correct, and for every new block you want to check that it's correct. Well, right now you just have to read the entire thing and check it's all valid and do everything. But you could maybe use a zero-knowledge proof instead, and maybe I could check the entire block is valid and make a proof that I checked the entire block, and then I can share this proof with you. And now you can, instead of checking the entire block, just verify the proof, and verifying them much faster. This is the scalability we had. So verifying the block is much faster by verifying the proof rather than doing the block directly. And this is the kind of basis for the ZK-EVM. Scroll's working on this. There's a team at the Ethereum Foundation working on this. There's others, ZK-Sync, doing similar kind of things. This is one of the things that I was complaining about a little bit, where we call it ZK-EVM because we're using zero-knowledge technology, but there's not actually zero-knowledge. We're just using the scalability property. To prevent a double spend in Ethereum, you just have to sealing. So you have to get rid of the zero knowledge, otherwise you can't apply this technology here. I'm not going to explain the ZK-EVM very well because I've not spent very long looking at it. I'm sure others could explain it much better than me in other places, but we'll just touch on it briefly. So there's also many reasons for the ZK-EVM. I'm just talking about checking the blocks because it's just a simpler thing to focus on. So we got a circuit that checks that all the EVM codes were followed properly. You're going to want to check that the block points to a valid previous block. You're going to want to check that the included transactions are all valid. You're going to want to check that all the EVM opcodes that are being called because they are from a signed transaction, and loads of other stuff. This is a very complex circuit or set of circuits that has to be made, and it's going to take a long time to build all those and make sure they all function well and don't have any holes in them. But those are no actual zero knowledge. It's all just using the scalability property. And I'm sure there are many links online that others could share about digging into this in a bit more detail. But the value of this circuit is that rather than spend all the computational power, every single node in the network using computational power to check everything, they can instead verify proofs, just save a lot of energy, save a lot of computational power, and just allow us to direct resources elsewhere and hope to reduce costs and things like that. Okay, I'm going to. Right, I asked this question, why do we not have knowledge? And I did kind of already say half the answer, but it's just something for you to think about as well. I'm going to skip this example and I'm going to jump to the last two non-examples and then just kind of conclude and then have time for questions. So like a non-example, I had friends at school, really I did, definitely was good. I can't prove this with zero knowledge proof. You can't just prove anything you want with zero knowledge proof. You can't just chuck zero knowledge at it. It doesn't work that way. You could make a system that does this. Maybe the school, they have like a monthly meeting and a consensus mechanism where the teachers, they all chat and then they're like, yeah, those two are friends, and then they sign a transaction, put it on chain, and then they do this for like all the kids at the school every month. And then later on, 10, 20 years, you've got the stuff on chain and you can prove that you were, that you had a friend because it's in there. But I can't do that because that didn't happen at my school. This should clearly never happen at any school. Yeah, but you could actually build like that. But then there's all this consensus stuff that goes on. So in that rough scenario where teachers meet, how do you know it's actually safe and secure? How do you know it's run well? If it's just done at one school, it's not going to be very secure. All the value of a zero knowledge proof is kind of wrapped up in external consensus mechanisms as well. We trust the consensus mechanism of blockchains. We've got a lot of evidence for it, a lot of good arguments. But depending on where else you apply zero knowledge proof, maybe like external context and consensus mechanisms that are important that don't work. And so you got to think about those as well. Okay. Last non-example, Tornado Cash. I'm sure we all know about. What they do is they mix your money and they use proofs. You just do it through Tornado Cash and then your money will be private. But imagine that they just built Tornado Cash. It just goes live. You're the first person to put in money. You put in 1 ETH, and then nobody else touches the contract. Before anybody else touches the contract, you spend that 1 ETH. Well, now we've just had one incoming transaction and then one outgoing transaction and nothing in between. So now obviously the only person the outgoing transaction could be is the person who put the money in there in the first place. So it's nothing wrong with it, just more context. And so zero knowledge proof don't just everything for us immediately. There's still other real world things that they make use of. And then I'm sure there's loads of other non-examples. Last two slides. One of the key takeaways is if you're trying to use the technology to solve a problem, you have to find the right circuit. What should the circuit do, and then what should the proof of that circuit tell you about the real world? Because if the proof doesn't make a comment in the real world, then it's essentially useless. So think about what functionality has to happen inside. Is there a hash function? Do you have to check values and numbers? Do you have to check Merkle tree inclusion and things like that? And then what values do you have to publicly reveal? So the root of a Merkle tree, the output of a hash function. You probably don't want to reveal the input of a hash function. And then there's things like knowledge asymmetry. So if you want privacy or the zero knowledge aspect, then this means that only the prover should know the certain knowledge and nobody else should, or at least the verifier shouldn't. So with the system you build where you want to integrate zero knowledge, why would the prover know this knowledge and nobody else would? You need additional communication mechanisms to make that happen. Is that feasible? Everything else wrapped up there. I didn't put this in the slides, but there's also the engineering work involved in making zero knowledge circuits is pretty hardcore. It's getting easier as we build out the landscape where rather than lay the gates out directly, you have things that build it for you. I can touch on those in another presentation if it makes sense, but there's Leo from Aleo, which will turn your Leo code, which is JavaScript into a Marlin circuit which is a proof system like PLONK. Yeah, so there's a lot to think about. And then final word is about trust. And like, zero knowledge remove the need for trust? Like, not really, but they do help. They do remove some requirements. Have to that the block is correct. I could verify the entire block, but I instead could just verify the proof. So by verifying the proof, I don't have to check the entire block. So it has helped somewhat. But then there's still like outside world trust, and the voting example I didn't have time for. A good place to see where the outside consensus mechanism really does matter for the proof, telling us what we the thing about the real world that we found important. Yeah, so those are the main things I want to give. Like I said, I wanted to make this kind of pedagogical different route compared to the other content that's out there, and I think this is more kind of messaging we should be spreading about zero knowledge, because it's helpful for people, and this is a foundation for actually thinking about how to apply the technology. It's not really just about like, oh, here's the polynomials and this is how we commit to them, and then we open them later and we combine them this way and you make it faster. Like, the vast majority of people don't really care. Some of us may find it interesting, but if we want to unlock more value from this technology, we need to like help it be spread and used in other places and used effectively, and not just as a buzzword that gets the money from VCs. Quick shill, we're organizing a conference again here next year in Istanbul. 2-day conference, 2-day hackathon. If you're interested in attending or speaking or sponsoring it, we'd love to chat with you. Please get in touch with me. And then if you want like more a follow-on lecture that touches more on the details of like things under the hood in PLONK or maybe Halo 2 and some other like zero knowledge related things and some more examples, just pester us and pester me, and then I can try and find some time to make more of them if you found this helpful. Thank you very much for listening, and if there are any questions, I guess we can start digging into those.
Oh, thank you, Errol. I thought that was excellent. That was really excellent.
Thank you.
Yeah, especially what the idea of there being a really big gap between the motivated learners and what's available, and trying to help more people understand how this, not just how it works, but like why it's useful to make
Yeah. I think one of the big problems is that like most of the people who are really good with this technology, they've got really well paid jobs trying to like build the stuff and improve the systems. They have like less time to make educational content, and they're used to explaining stuff to technical people and to VCs and this kind of stuff where they're really like explaining the details. But for other people, that isn't the messaging that we need. And yeah, so these people, the smart people who can explain it, they've really like mindlessly said their messaging system to explain it at this level, but that's the wrong level for us. So we've got to spend a bit more time trying to take it in other directions. And others do good work in this direction as well. I mean, like ZK podcast, ZK Hack, and Rose, and I'm sure there's plenty others that I'm not able to properly credit.
Yeah, and we reached the Discord limit for streaming for the first time. That's not us, that's the Discord. And then on Twitch, we had like 16 people watching. So it's pretty popular, and people like the YouTube also. So I just dropped a bunch of links to Errol's Twitter and some of the things he's written. And I'm also going to include a survey if everyone could help fill that out. If you're interested in talks like these or hearing more from Errol, just let us know in the survey. And also there's collecting feedback for the Applied ZKP website, which you can find the prototype testing channel. I'll also drop the link in there. So now if anybody has any questions, you can unmute and ask or type it into the chat.
Thanks. If there's other questions on the Twitch stream, if people could copy that over, that'd be helpful. I'll just quickly say this this blog post that is here from Node 101 that I wrote. This is basically just based off this blog post that I wrote. I hopefully, turning a 20 into a 40-minute presentation adding. But this, if you like this, is in your time. This question from Kanu: does semaphore use is semaphore's use of generalized proofs a good example? Yeah, I think it's a really good example. I don't know exactly how they make use of it there. My rough understanding of semaphore, which I should look into more, is a kind of signaling system. I think they use generalized proofs for like Merkle tree. They use nullifiers. It is a very good example. I'm fairly sure of that. I'm pretty sure it uses zero knowledge proofs and not just other tools. Maybe somebody else could help elaborate, but that could actually be a really good example to dig into in much more detail in a talk or a blog post. So that wasn't a very good answer, but I think so. I guess we can just give it a... Huh? Okay, I didn't quite hear that.
Could you repeat that, Joe?
Yeah, Istanbul event info. I would love to. We don't have a website yet. I'm okay. I'm trying to help this grow and build it and get good speakers. I'm just gonna drop in, and if you're interested, please just message me, and then I will, like, as soon as things are ready, I will send you the website and stuff like that. We're trying to grow the community here. We did like a one-day event this past summer, but taking time. There probably are blog posts for Semaphore. I haven't seen them. I haven't looked at it too much. But if someone can find them, it might be a good time to drop it in the chat. Okay, I'll just wait for these last people who are typing to finish, and then we'll know whether there's more questions or not. So I think there aren't any more questions. If there are, I will just try and like look in the chat. But I think if not, then other people want to head off. So thank you once again for coming. Pester us if you want more from me or from others from this.
Sorry, Errol, there's two questions in the chat. The last two questions, if you don't mind.
Okay, there's this question here. Sorry, I didn't hear what people were saying. But there's asking if there are any constraints on creating circuits. Some of the stuff I didn't mention that I can expand upon in later on is that I said there's this addition and multiplication gate in PLONK. It's not actually quite true. First, you can make other type of gates. You can define gates that do whatever you want. You don't want to be too complex, otherwise it will slow things down. But also, these gates don't actually exist. It's actually just a table of values, and it's how you interact with that table that you get these properties. So I said that the gates were ephemeral, didn't really exist. They're actually numbers in a table, and yeah, you can do stuff. There's constraints on like what's possible because they have to be mathematical things, but you can add more complexity. And then in terms of creating circuits, constraints for making circuits is just like there's practical constraints of like if it's too big, the circuit's too big, there's too many gates, and too complex gates, it will take too long to make. So for example, with ZK-EVM for Ethereum, you need to make a proof quite quickly. Is it 10-second block times for Ethereum? So you need to make a proof of the block within a second, and if you can't do that, then the technology can't be applied there. So there's lots of like real world constraints about whether a circuit is feasible or not. Tornado Finish white paper. Oh, cool. Thanks, share. Okay, I'll see if there's a follow-up question from Kano. So I think for post links being shared in the chat. I think they're here forever. So if people watch this later or want to find these links later, they can just come back to this chat, which is the public chat stage in the PSE Discord. And there's some cool links being shared here. I mean, I want to look through this at some point as well. Okay, just waiting for these last two comments to see if there are. Yeah. Oh, is this link for Tornado Cache from now and S? Is it just now on CS Explainer? I made a video on this. No, I'm just going to shill my own video because I put a lot of. I use like 3 Brown for making videos, and I put a lot of work in. So maybe people will like the visual through anything in HQ. Trouble is, I only made one of them, so I didn't like get the benefits of getting better at making. Oh, so the setup is okay. What's the best place to start for a trusted setup? This will be very good content for the next talk as well. It's kind of hard to summarize too quickly. For each gate, when you set up, let's assume it's a universal one, and you know what that means another time. But you need numbers from like you'll go from numbers 1 up to like 10 and 10 million or 100 million. There is a I can no. I think you can individually mute people who have left on their mics by accident. Yeah. I think it might be better to wait and explain these in more depth and more effectively in others. I'm actually just going to make a quick note of some of these topics for another talk, for our next talk. So I think it's a good time to, leave it there. Thank you once again. Feel free to reach out to me individually for questions about this or Istanbul, and also put questions in the chat and I can answer them for everybody to see too. Cheers.
Thank you.
Have a good day and a good weekend.
You too. Thank you.
Cheers.